Welcome back, students. In this video segment, we'll take a look at one section, section 12.6, cylinders and quadric surfaces. Not quadratic surfaces, quadric surfaces. The name quadric and quadratic are very close sounding, and they're also pretty close in meaning, but we'll get to all that. In this section, we're going to take a look at what I think is one of the more difficult things for me for the course, and that's to graph objects in 3 space, specifically surfaces. I've been doing this for a whole long time. As of this video, I've been teaching calculus for about 30 years, and it's never gotten easy, the idea of graphing a surface. The reason I'm bringing this up is that I don't want you to make this a deal breaker for the course in terms of deciding whether you're going to be successful or not. If you're not able to come up with really perfect graphs of things, don't worry about it. Don't worry about it. Do the best you can. If you're not sure that the graph that you produce is conveying to the reader, or I guess more importantly for you, the grader, just to write in words what you are trying to convey with your graph. Okay, so if your graph doesn't make sense to you, then write out in words a description of what you're trying to convey by your graph, and that description combined with your graph should turn out just fine. But I think you may surprise yourself. Very typically, students tend to do better at graphing than I do. I'm not an artist. I don't claim to be, in fact, the farthest thing from it. But anyway, so let's just go ahead and get started. The first topic, cylinders. Cylinders. You might think, well, what could there be? What else could there be to cylinders? Why do we need to talk about cylinders? Well, the idea of a cylinder is not just the one that you might be familiar with. So, for example, suppose we consider the equation x squared plus y squared equals 1 in R3. We looked at this earlier in the course. This is in R2, of course, it's a graph of the unit circle centered at the origin. We grew up with this circle in pre-calc and in algebra, and then it held together a whole bunch of trig. Well, in R3, if you'll recall, it represents a cylinder. It represents a cylinder because it represents a circle in the xy plane, but the z coordinate, or the z coordinate's missing from this, so the z can take on any values. So as long as the x and y stay on the circle, the z values can go up and down, and that pretty much describes a cylinder. The graph of the cylinder might look something like this. And I'm going to try not to stop the video and produce the graphs so that we can keep this real and you can see how I form graphs. So to graph this cylinder, I might try to draw first a circle in perspective, and I might erase it and then try it again until I'm satisfied with a flat circle. So this circle is viewed as flat, and you kind of see it as parallel to the xy plane. And then here's the left edge of the cylinder, the right edge of the cylinder, and then another portion of the cylinder. A dotted line indicates we can't see that. It's that we're looking at that portion of the cylinder that's behind us. And then what I do is I introduce the axes. So I might then, oh gosh, I have color choices here. I might then introduce the axes. So here's the y-axis. Here's the z-axis, and here's the x-axis. So after all these years of doing this seems to work out better for me, to actually draw the cylinder and then draw the axes in later. Okay, and as I mentioned, and we've talked about this before, it's a cylinder because as long as x and y stay on the circle, z can go up or down. And that generates the cylinder. I've only drawn the cylinder for z more than or equal, greater than or equal to 0. So the cylinder extends infinitely in both directions. I want to take a different look at this cylinder, because this cylinder that we've drawn, or I've drawn, is only one example of something more general that we also refer to as a cylinder. We'll get to that in a second, but I'd like you to consider defining this cylinder in a way that might seem a little unnatural at first. Okay, first of all, here's a flat plane. You could view it as the XY plane. Here's a flat plane. Let me fix this a little bit. Here is a plane, and I'm leaving the back and the right edge out on purpose. Here is, and you can view this as the XY plane. Here is the circle in the XY plane. Okay, so the cylinder can be thought of as that surface that consists of that circle and one line. I'm drawing it as the left edge, but it doesn't have to be the left edge of the cylinder. And all other lines that are parallel to that line that pass through the curve in the XY plane, the circle. Okay, I'm going to repeat that again. The cylinder you can view as the surface that consists of all lines that are parallel to the one I've drawn, the little line, the little vertical line on the left there, parallel to that, and pass through the given plane curve. Okay, so I'm going to put the upper circle in for perspective, but then, oops, I'm going to draw a little bigger. I'm going to draw it a little too big. That's okay. But then go back to what I just said. Suppose that little circle above is not there. The circle below, the one line on the left, and all the other lines that are parallel to that line that happen to pass through that first circle in the plane below. And that is the definition. That is the definition of a cylinder. It's a curve, a line that passes through that curve, and all the other lines that pass through that curve that are parallel to that first line. If you missed that, I have it written out for us. This is from our text. A cylinder is a surface, and as I go through this, I'm going to actually draw what's going on here. So here's that plane that we're starting out in. It's a cylinder is a surface that consists of all lines, and we call those lines rulings, that are parallel to a given line and pass through a given plane curve. So here's a given plane curve, sort of an S-shaped curve-ish thing. Okay, and here's that first line, the given line. Now go back to the definition. A surface that consists of all lines that are parallel to that one I've just drawn and pass through the given plane curve that I've just drawn. So imagine a whole bunch of other lines passing through that curve that are parallel to that curve, and that's a cylinder. So there's one over here. There's one over here. There's one over here. And that's kind of how we're going to get the upper sort of band here. And then there's all the other ones. I'm drawing just a few of them. All of these little red lines are parallel to that original line I drew. And I'll go back and finish my plane. Okay. So what is a cylinder? It's like this. Imagine you're wearing a leather belt, and you take the belt off and you hold your pants up so that your pants don't fall down. And you put that belt on the table, and sort of put it out in the form of a snake, but have the edge coming up, have the edge of the belt perpendicular, not even perpendicular to the table. It's like laying a belt out on a table. You get a cylinder. I don't know if I like my analogy. That's the definition of a cylinder. What a squiggly little thing is a cylinder. It doesn't have to be closed. It doesn't have to be perpendicular to the plane on which the curve, the original curve lies. So with that in mind, this next equation is also a cylinder. Now think about that. Think about that for a minute. In R2, this is not a cylinder, it's a line. That you should know. Actually, I'll be more firm. You must know. This is like a real basic line. In R2, this is a line. That's really a no-brainer. I know that. It's the line that passes through y equals 1 as an y-intercept and x equals 1 as intercept. Okay. In R3, this is something that we looked at in the last section. This is a plane. This is a plane. Okay, we know a lot more about this plane. We know a normal vector and everything else. It's a plane. You could write this as x plus y plus 0 z equals 1. You could write coefficients of x and y. You have a normal vector of 1, 1, 0, etc., etc., etc. This is a plane. The plane. Oops. It was a plane. Well, not a pound, but a plane in R3. Okay. Now let's take a look at that plane in R3. That plane in R3 is very easy to draw, relatively easy to draw. Okay, so I'm going to start out with the first octant. Here's the first octant. So here's x, here's y, here's z. And again, I'm going to try to do most of this on camera and not try to real carefully draw things off camera and then throw them in front of you, because you guys are going to be drawing. You're going to be needing to draw this stuff. So I need to show you how to do this. So let's draw that line that I just drew, the line above in the xy plane. Let's draw that in the corresponding portion of 3 space. Here's x equals 1. Here's y equals 1. I'm only going to draw a portion of that line in the first octant. So here. Now remember, the definition of a cylinder just off to the side here. Oops. It has a curve. It has, I'd like to draw a little better curve. Oh well, it's the best I'm going to do. It consists of a curve. Here's the plane. There's the curve. Now what I've just drawn in the xy plane, x plus y equals 1, that's the curve. And a whole bunch of, what else does a cylinder consist of? A whole bunch of lines that are parallel to a given line that passes through the curve. There's the given line. And there are the other ones. There are the, oh dear. So x plus y equals 1 is missing the z coordinate. It's missing the z variable. So it is a vertical plane. It extends in the z direction. Extends in the z direction. Okay, so there's the plane. Of course, it extends infinitely up, and I haven't drawn any of the part that extends down. It's a vertical plane. Now, a vertical plane is also a cylinder. This is also considered a cylinder. It satisfies the definition of a cylinder. Okay. Where are the other lines? Well, here they are if you want them in red. Here are the other lines. Here you go. You get this striped wall or whatever. Not really striped. It's kind of thick. Okay, so we're generalizing the concept of cylinder to include a whole bunch of other surfaces. Okay, so I think this is probably going to be the easiest portion of the section though, and I think you're going to get good at just a little predictor. I think you're going to get good at cylinders pretty fast. Okay. So how do you tell if you have a cylinder or something else? That's a big deal. As we go through the course, you're going to notice that the materials get more and more and more elaborate, and they require previous materials. So we gotta be able to come up with graphs of surfaces very soon in other sections, other chapters. How do we tell what kind of graph we have ahead of time? Well, here's one way. Sketch. Let's say part A. C equals x squared. Now I know that's a cylinder, and you will too, and you'll be able to tell how in just a few seconds. I know that's a cylinder. Why? It's missing a variable. So remember the plane above? It was missing the z variable, so it extends in the z direction. This is missing the y variable, so pay attention to this. So this is a cylinder that extends in the y direction. What curve does it go through? It goes through the parabola z equals x squared. Z equals x squared is a parabola just like y equals x squared is a parabola. Y equals x squared is a parabola in the xy plane. Z is a parabola in the xz plane. Okay, so this is a cylinder that passes through the parabola z equals x squared in the xz plane, and extends in the y direction, extends in the direction of the missing variable. Okay, if you've missed that, I'm going to draw it for you, so don't panic, okay? So how do you draw a cylinder? Well, you can draw your cylinders any way you're comfortable with. I'm not going to insist that you draw things the way I draw things, but I'll give you my drawings as suggestions, and you take them or leave them. If you have a better way of drawing these things, fine. Or even if you don't have one and you develop a better way for yourself, that's good. This is not about me. This is mostly about you guys, okay? Learning this stuff. So here are the y and z axes. Here's the x-axis. I'm going to give you a suggestion of how I would graph the cylinder. Okay, so here's 3 space. The first thing I would do is graph z equals x squared as a curve in the xz plane. Oops, look at that, I drew the y-axis vertical. I bet you've done that too. If you haven't, then I lost the bet. But I bet you've done that too. We're used to putting the vertical axis as the y-axis. At least I am. In any case, anyway. So what does this look like, and how do we draw it in the xz plane? Well, here's the xz plane moved off to the side. This parabola should be automatic to you. Z equals x squared looks just like y equals x squared, except it's in the xz plane instead of the xy plane. It goes through the point x equals 1, z equals 1, x equals negative 1, z equals positive 1, and does that. So first, draw that in 3 space. Okay, I would suggest drawing, see this little red dotted line. I would suggest drawing that first in 3 space. So I would suggest drawing that first. What's it going to look like in 3 space? There it is. Z equals 1. Z equals 1. Okay. So here's about x equals 1. Here's about x equals negative 1. Go up to z equals 1. Go up to z equals 1. And this is where it gets tricky for me. Let's try to actually draw this in perspective. So there's the parabola, z equals x squared. Okay. So next what? You could draw a ruling. You could draw a line and I'll even do it. Let me get rid of this little graph out to the side here. You could draw one of the rulings first. You could draw one of the rulings first. You can draw that one. Oops, maybe draw it a little better. Draw. There's one. But I wouldn't. You could leave it there if you want, but I wouldn't. I'm going to extend the x-axis a little longer. All right. What I would do is I would draw a copy of what I just drew in the y direction, moved over far enough so that it won't get in the way. I'll explain that get in the way business in a second. So here's a copy of the x-axis. Here's a copy of the z-axis. I'm going to draw another copy of my graph. Here's a copy of that little red dotted line. Oops, that's all right. Here's, let's see if I can do this decently. Here's z equals 1. So here's a copy of that same curve. Just move to the right a little bit. Okay. The reason I did that is that I'd like to give my rulings something to pass through. Now draw that ruling. This is a cylinder that extends in the direction of the missing variable. Missing variable's y. Kind of missed. Missing variable's y. Now do you see a sort of trough or rain gutter or whatever? That's a cylinder. Hopefully you see it too. If you don't see it right away, then draw some more rulings in. You can even change colors, or you can put them in dotted or whatever. I'll put them in blue. Let's see. Here's another ruling. Here's another ruling. Here's another ruling. Here's one on this side. Here's one on this side. Here's one on this side. And they just kind of disappear from us and from view. So, do you see it? Hopefully you do. You see a sort of a rain gutter extending in the y direction. Okay, of course it opens up in the z direction infinitely, but we just drew a little piece. Okay, and then maybe I'll come back and identify this as the y-axis. So you notice my drawing, it's not that nice. It's not that nice, but it's the absolute best I can do. I've drawn this over and over and over and over and over and over and over for 3 decades. Most of you aren't even close to 3 decades old, and I've been drawing this over and over and over and over. And actually, not for 3 decades. I've been teaching for 30 years, but my math education goes, yeah, I'm really old. Oh my goodness, I'm old. I don't mind being old because I like being alive. Okay, so let's take a look at another one. C equals cosine of y. Okay, now I'm going to start this out with the sentence I said before. I know that this is a cylinder. Why? It's an equation in 2 variables. Equations in 2 variables give curves in 2 space. So it's an equation in 2 variables. You already know that. How do you know that? You took pre-calculus, you took algebra 2, you took trig, you took calc 1 and 2, and the things you were drawing had 2 variables in them, the curves. Okay, so this is a curve, but it's missing the x variable, so it's a cylinder that extends in the x direction. These are the hardest things for me to draw. It's hardest to draw things that are coming out of the page, or as I would say in a classroom, out of the board. The x-axis is coming out of the page. Okay, so I just do this ultra carefully. Okay, so how do we start it? Well, we just did. We have an idea of what it's going to look like. It's going to look like a cylinder that extends in the x direction, a rain gutter, if you will, that extends in the x direction. They don't all look like rain gutters, but whatever. Okay. So here's the YZ plane. I think I'll make it a little smaller. Here's the new YZ plane. It turned out about the same size. That's okay. Yeah, move it over a little bit. Okay, here's the YZ plane. And where's my x-axis? I'm going to put that x-axis in later. Why am I going to put it later? Because this curve, the curve z equals cosine y, lies in the yz plane. I can extend the y-axis a little longer. And then graph z equals cosine y. Okay, newsflash. This should be automatic. That was a joke. Well, the newsflash part was. The part that this should be automatic is not a joke. Z equals cosine y. I'll just draw one period. Here is, oops. Here is a little box between y between 0 and 2 pi. So I'm going to draw one period. So here's 1 pi, here's pi over 2, here's 3 pi over 2. Cosine starts on the axis, goes through 0, then goes through -1, then goes through 0, and goes back to 1. So here's an approximate graph of the cosine function. Ugh, already started out awful. It'll be okay. Again, I'm going to try to keep it real. No, I was going to say no redraws, but I guess I am doing redraws. Okay, so here's the cosine function for y between 0 and 2 pi. Now let's draw an x-axis in here. Let's get an x-axis in here. Here's a perfectly good x-axis. Make it a little longer maybe. Okay. I'm going to draw a copy of this same graph forward along the x-axis a little ways. And I drew a long x-axis because I'm going to draw it forward a ways enough so that it doesn't get in the way of my other graph. I don't want to draw it, let's say, right here, because if I draw a copy of that, it's going to hide the graph that I just drew behind it. I won't be able to see it. Okay, so I'm going to come, how far forward? You'll experiment. You'll discover for yourself what's good. And then I'm going to draw a little dotted y-axis, a little dotted z-axis. Let's see. So here's 2 pi. Okay. So I'm going to come up 1 unit. All these little dotted lines you don't have to put in if you don't need them. I need them because my graphs really stray. Okay, so here's pi over 2, oh sorry, pi, here's pi over 2, 3 pi over 2, here's, so let's draw this cosine function again. Ooh, again we start out with not a good, we'll just take it. And the other portion. Okay, so we have another copy of it, forward. Forward meaning in the x direction. Now, draw a few rulings. Draw enough rulings so that you and whoever's looking at this, whoever else is looking at this, can see a cylinder that extends in the x direction. And you can draw your rulings with different colors to make things show up. Maybe I'll draw one of them in black. Yeah, okay. I'll draw the first one in black. I'll draw the second one in black, way up over here. Guess I'm drawing them all in black now, huh? Here's the next one. I missed. There we are. There it is. Close enough. You see it? No? Yes? Like you can, like I can hear you. And then if you can't see it, draw some more. This would be enough, by the way, for me. I see it. This would be enough for me, maybe with a couple more to know that what you're trying to convey to me is, in fact, what we're seeing. This one's going to be kind of funky. Okay. Well, now I see it. You can draw some more rulings if you want. You can draw a whole bunch of rulings. You can draw a few rulings. It's up to you. Okay, I'll stop there. You can keep this going, and hopefully you see a wave that is extending constant in the x direction. The z values are constant in the x direction, and it's wavy in the y direction. Okay. Okay. Your graphs don't need to be perfect. Some of your graphs, some of you guys' graphs are going to be perfect. And I hate you. No, I really don't hate you. I just wish I had that skill. Most of your graphs are going to be better than mine, but somewhere in between better than mine and really, 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 really nice, like some of your classmates are. So don't worry about it. If your graph doesn't look good, then describe in words what you would like. Describe in words what you don't think your graph conveys, so that you sort of fill in the gaps between your picture and what you intend would be. Okay. This we spent a little time on this. We spent what was on this? Half an hour on this. We spent a little time on this. But this is a small part of the section. The biggest part of the section has to do with these things called quadric surfaces. Quadric surfaces. Okay. So what is a quadric surface? Okay. Well, in pre-calc you studied something called conic sections. Okay, so here I'm still in blue. So from pre-calculus, you studied conic sections. Conic sections. Conic sections are curves. They're curves. They are curves that start out of the form, the general form, ax squared plus by squared plus cx plus dy plus e equals 0, where a, b, c, d, and e are constants, not all of which are 0. In fact, we can't have all of a, b, c, d, and not 0, so we kind of need some constants. But you can tell what these things represent for different values of the constants. Suppose c and d are 0. C and d are 0. A and b are 1. A and b are 1. C and d are 0, and e is negative 1. Unit circle, bring the 1 over. Now suppose a is 1/4. B is 1/9, and C and D are 0, and E is negative 1. This is an ellipse. Okay, so this is I know you know this, and you've studied this before, but in pre-calc it's usually toward the end of the course, and you're getting ready for your final and stuff like that, so you may not remember it right off. Is another example. Let's say A is 1, B is 0, C is 0, D is negative 1, and E is 0. It's a parabola. Okay, suppose A is 1, B is negative 1. This is where your memory might get a little fuzzy. C and D are 0, and E is negative 1. C and D are 0, E is negative 1. X squared minus y squared equals 1. What is it? Well, good news, bad news. The bad news first. You have to be able to graph this curve very quickly. That's the bad news. And the further bad news, you've very likely forgotten, or it's fuzzy it's fuzzy in your mind right now what this is. A hyperbola that opens in the direction of the x-axis. Okay. The good news is that we're going to be seeing these conic sections when we draw these new things called quadric surfaces. They're very important part of quadric surfaces. And the further good news is you have infinite resources on the internet. I think you can do Wikipedia Wikipedia search for conic sections, and you get a wonderful review and stuff like that. But don't ignore it, because we kind of need to know this. Again, the last curve is a hyperbola. Specifically, its asymptotes go through the square that has intercepts 1 and -1. This is not meant to be teaching you how to graph hyperbolas. You're supposed to know this. It's just a reminder. And it opens to the right. If y squared term had come first, it would open up and down. Okay. So those are the fancy term for those curves: hyperbolas, parabolas, ellipses, circles. They're called conic sections. There are a couple of other conic sections. They're called degenerate conics. We don't need to get into that though. Okay. Back to our course. In our course, we talk about a related surface. They're called quadric surfaces. Quadric surfaces. Now, before I give you the general equation of quadric surfaces, I want to address, so how do we graph them? We graph them in a very similar way that we graphed conic sections. We memorize what certain forms are, the graphs of certain forms are, and then we look at the specific equation to get some fine detail. Specifically, I knew that was a hyperbola, and from the work that we did earlier, that this was a hyperbola, and I know that from the work we did in pre-calc that where the asymptotes lie, so I connect the asymptotes. I draw the asymptotes, then the hyperbola. I know that y equals x squared is a parabola. Why? Because I memorized it. I know that it should go through 1, 1, -1, 1, and I get its graph. Memory. The ellipse. I look under x, take the square root of 4, I get +2 and -2, 2 square roots of 4. I take both square roots of 9, plus or minus 3. This is not meant to teach you. This is meant to a quick reminder of how we get the graphs. So see how my graphs are ugly, ugly, ugly. Anyways, this is how we graphed. At least this is how I teach my pre-calc students to graph conic sections. You memorize the forms. You absolutely memorize the forms, and then you draw a few points and connect dots in the shape that you memorized. That's how we're going to graph quadric surfaces, similar to how we're going to graph quadric surfaces. So what are quadric surfaces? The general equation? It's almost a waste of time to mention it, but it's not quite a waste of time. But I want to mention it. The general equation looks like ax squared plus by squared plus cz squared. It's starting very similar to the conic section, plus dxy plus let's say eyz plus f, what's missing, xz. I can clean that up a little bit. Oops. I can clean that up a lot. EYZ plus FXZ. There's more. Plus CX. This is the bad news. See if I'm doing this. CX plus, oh no, GX plus HY plus IZ. My God, we're going through the alphabet. Plus J equals 0. My goodness. So why is it called quadric? Highest power x squared. Highest power y squared. XY is considered to have degree 2 also. multiply a variable times a variable. The polynomial that's formed has degree 2. So it's sort of like quadratic, but it's quadric. Now, for us, we're going to be looking at our surfaces that don't have the cross product term. Not like cross product vectors, but x, y, y, z, x, z. The cross product terms, and you may know this if you covered it in pre-calc, but the cross product terms, they tend to tilt or rotate the curve or surface that you're graphing. And we're not going to rotate these things. Okay. Now, you don't need to memorize this general form. This is just to introduce you to what it is we're doing. We're going to look at very specific standard forms. And we're going to start right off. We're going to, with a specific quadric surface. So, for example, sketch. And the quadric surface is going to be z squared equals, oops, not plus, z squared equals x squared plus y squared. Z squared equals x squared plus y squared. So it's the general idea of how to graph. How do we approach graphing quadric surfaces? Well, the idea is to look for the intersection of the surface in question with planes. Just stop the sentence there. Look for the intersection of the surface with planes. Okay, but those planes are going to be special planes. They're going to be parallel to the different coordinate planes, parallel to the xy, the xz, and the yz plane. These are called traces. These are called traces. Before we dig into the surface I just mentioned, z squared equals x squared plus y squared, suppose that the cross section or the intersection of the surface I'm looking at with the plane z equals 1, horizontal plane z equals 1, is a circle. So this you're looking at, this is the intersection. Here's the plane z equals 1. Here's the intersection of the surface with the plane z equals 1. Okay, and suppose that if we look at the intersection of the surface with the plane x equals 0, x equals, what is x equals 0? X equals 0, that's the yz plane. So suppose that here's the yz plane, the intersection of the surface with the yz plane turns out to look like this. A parabola. So now your brain puts both of these, our brains put both of these two traces, these two-dimensional traces together, and we see a cup that opens upward. We see, just taking away the planes, we see this. If when, as you draw these things, or these surfaces, your traces don't reveal to your brain what you should be seeing, or a surface, then draw more traces. If I were to draw with the intersection of the surface with the plane z equals 1/2, I might see this. With z equals 1/4, I might see this. Okay. If I found the initial trace with z equals 1, the cross section with the surface with z equals 1 with a circle, horizontal circle there, and the trace in the plane, in the yz plane, it was a sort of a, we call it a twisted cubic, but it's sort of this curve sort of has a sharp edge. And if I drew a few more traces, if necessary, we might see sort of this hurricane-shaped thing, or this sort of a, not hurricane, a tornado-shaped figure. My rough drawings here weren't meant to be any kind of a detailed idea, or detailed explanation. But what we're looking at is basically slicing through our surface with a knife, and the knives that we're slicing through our surface need to be parallel to the x, y, xz, and yz plane. Not all at once, that's impossible. Maybe separately. So let's return to Z squared equals x squared plus y squared. So back to z squared equals x squared plus y squared. Let's begin. Let's take a look at what happens when I intersect the surface with the plane z equals 1. Okay, so let's look at, in fancier terms, let's look at the trace of this surface in the plane z equals 1. Z equals 1 is a horizontal plane. Okay, so how do you do that? You substitute z equals 1 into the equation. You get 1 squared equals x squared plus y squared. Now, in a plane, what's that an equation of? It's the same old unit circle that we've been dealing with all along. All along in our whole math careers, actually. So here, so far, let's draw this trace. Well, here's the xy axes. Here's the the y and z axes. Here's the x axis coming out forward. And in the plane z equals 1, so here's where z equals 1 is, right there. In that plane, let's draw a circle. So here's a circle. This is drawn in the plane z equals 1. Okay. Well, I notice in this equation z is squared. I notice that z is squared. It's the ugliest looking arrow I've drawn today. It's getting worse. I'm obsessing over it. Okay, this doesn't look like an arrow anymore. Look at the original equation. Z is squared. If I were to let x z equals -1, I would get the same trace. So let's try that. Let's let z equals -1. I also get -1 squared equals x squared plus y squared, which is still x squared plus y squared equals 1, which is still a circle. But that circle is located in a very different place than the original trace was located. It's located in the plane z equals -1. So let's draw this in the plane z equals -1. It's going to be kind of a miracle if I get a nice exact copy of my first one. But we'll see. Here's z equals -1. Here's z equals the original +1. Here's z equals -1. Okay, so at z equals -1, I want to draw a circle. This dotted line is just to keep my circle with the same radius. Okay, it's okay. Oops. Okay, so now we have two traces. This is not a cylinder. Those dotted lines are not part of my drawing. In fact, maybe I should get rid of them. Dotted line is not part of my drawing. Okay, so far I have two cross sections. Is this enough to tell what the three-dimensional surface? No, heck no. Draw more traces. Let's take a look at what happens when I slice through this with a knife that is exactly in the direction of the YZ plane. What's the equation of the YZ plane? Oh, that's a good question. Well, in the YZ plane, what does every point in the YZ plane have in common? X equals what? 0. That's the equation of the YZ plane. So now let's take a look at the trace of the surface in the plane x equals 0. Okay. Well, what do you get when you let x equal 0? You get z squared equals x squared plus y squared. You get z equals plus or minus y. Those are two lines. One with a slope of +1, z equals y. One with a slope of -1, z equals -y. So draw those two traces. Here's one of them. Z equals y. Z equals -y. Now what do you see? Might be able to fix it up even more if I put some dotted oops, oh, I still have it on an eraser. That's why it's erasing. It's like, why the heck is it erasing? Let's put some dotted lines where we can't see from our perspective. What do you see? You see two cones. One opens up, one opens down. The two cones together are called one cone. It's called a cone. You don't have to call it a double cone. A cone is not necessarily just one portion. If you have a cone that opens up combined with a cone that opens down, you get a cone. It's a cone. It's a cone. If you weren't sure that this was a cone, you could draw more traces. Draw more traces. Let z equals 1/2. You'd get the line, or sorry, the circle x squared plus y squared, z equals 1/2. So the x squared plus y squared equals 1/4. I'll put it in. If I let z, I'm going to put it in red. If I let z equal 1/2, I get the line x squared, or sorry, the circle. I keep calling it a line. The circle x squared plus y squared equals 1/4. If I let it, if I could keep doing this, if I let z equal 1/4, I'd get another circle. The bottom line here is they draw enough traces. This is really important. You draw enough traces so that when you connect the traces, you have a surface that you predicted. There's something missing here, though. You draw enough traces so that when you've drawn the traces, you see a surface that is the surface that you predicted. I never started predicting this was a cone. So here, back to how do we graph quadric surfaces? The similar way we graph conic tectonic sections. We memorize certain forms. We memorize general forms. The general form of a cone with axis vertical, with axis the z-axis, is, we simply memorize this, z squared. It's going to look like z, like what we just started off with, z squared equals x squared plus y squared, but that's not the general one, that's a specific one. The general one is z squared over c squared equals x squared over a squared plus y squared over b squared. Okay, and this is called a cone. This is a cone. Okay, when you change a, b, and c, you change the cross section of the cone to being different circles, or more generally, here's a sort of a good spot check for you if you remember your conic sections. If z equals a constant, what do we get? What do we get with z equals constant? X squared over a squared plus y squared equal b over b squared equals a constant. Those are ellipses. So these cones can have cross sections of circles, but they could also have cross sections of ellipses, and we still call them cones. Okay. So what if we don't have this exact form? What if we have y squared equals x squared plus z squared? This is still a cone. This is still a cone. It's still in exactly the same form. Variable squared over constant squared equals variable squared over constant squared plus another variable squared over constant squared. It's a cone, but the axis of the cone is not the same. Look back at our form. The axis of our cone was the z-axis, and that's the variable that was first. So this is going to be a cone, and the axis of this cone, is what? The y-axis. Now stop there for a minute. Slow down there for a minute. we're looking at a cone. And you memorize the shape of a cone. A cone is this guy. Ugh, that's a cone. That's a cone with the axis as the z-axis. So what is a cone with the axis as the y-axis? That's the shape. It's a little ugly shape I've drawn, but that's the shape of our object. You go into this knowing that this is a cone. And what do you need to, what kind of traces do you need to graph a cone? You need only a few. You need this circle, you need this circle, and you need these two edges. That's all you need to draw the cone. But you know that the cone has as its axis the y-axis because the y variable comes first. So when you're graphing your traces, then, I'm recycling this graph over again, you're going to first graph the trace, the circle that I'm making solid here, in the plane y equals a constant, y equals 1. So try letting y equal 1. How did I get y equal 1? Look at the variable here. Y equals 1. If I let y equals 1, I get 1 equals x squared plus z squared. So I graph that. 1 equals x squared plus z squared. And keep in mind, I already know what the shape of this thing is because I predicted it, because it's just a general form of a cone with the variables switched around. Okay, so here's 3 space. Let me extend the y-axis a little further. Here's y equals 1. Now in the plane y equals 1, draw a circle. And here's z equals 1, about proximate. Here's z equals -1, proximate. Draw a circle. I can do that edge a little better. So there's the circle on the right, the trace on the right. What should I let y equal now? Let y equal -1. Identify this trace. This is at y equals -1. So let y equal -1 in the equation. So I'm looking at the trace of the surface, this fancy terminology, trace of the surface in the plane y equals -1. So I'm going to get, well, what's the equation? Y squared equals x squared plus z squared. Y squared, -1 squared equals, x squared plus z squared. It's the same equation I got in the previous trace. It's a circle, but it's now in the plane y equals -1. So y equals -1, go up +1 in the z direction, -1, go to -1 in the z direction, draw a circle. Why am I drawing this dotted? Because I know I'm not going to be able to see it. How do I know that? Because I know that this is a cone, and from my perspective, I know I'm not going to be able to see that. Now I'm going to get rid of the x-axis temporarily. I'll put it back. It's going to get in the way of my final traces. I need the 2 lines that are going to complete this view for me. Those 2 lines lie in the yz plane. In the yz plane, x equals 0. In the yz plane, x equals 0. So let's let x equal 0. Keep in mind, I did remove the x-axis temporarily, but let's let x equal 0. And the x equals 0, I get, what's the equation of this surface? It's y squared equals x squared plus z squared. So I get y squared equals 0 squared plus z squared, or y squared equals z squared. in the YZ plane, those are two lines. Y equals plus or minus Z. One with a positive slope, one with a negative slope. And I see a cone that's opening to the right and left. I miss my x-axis. I miss it. So I'll put it back in. Here's the x-axis. Okay, that's how things work. You memorize the form. If the variables of the equation that you're given are moved around, that's not going to change the shape of the surface, but it's going to change the orientation of the surface. You memorize specifically that z squared over c squared, you memorize this, equals x squared over a squared plus y squared over b squared. Those are cones. Cones with vertical axis, z-axis is the axis. Okay, this is how this works. So for the rest of the lecture, we're going to be looking at several other standard forms that are going to get you through first the homework, and then ultimately when we start working with these surfaces, when we do multiple integration, we're finding volumes of solids and stuff like that, you can get graphs of these surfaces very quickly or relatively quickly. Okay, you don't graph surfaces, by the way, by plotting a few points and connecting dots. Almost never do we do that. The same thing with curves, and we don't graph curves by plotting points, making a table of points and connecting dots. We did that in Algebra 1, and that's it. Okay, so how did you graph curves? Well, you took Calc 1, and you figured out where the curve was increasing and decreasing as maxes and mins, concave up, concave down, points of inflection, asymptotes, all that stuff. Okay, so similar thing here. We're starting out real gentle here. You basically memorize forms of shapes, then you fine-tune them by looking at traces. Okay, so let's move forward. So next, example sketch. By the way, the author of your textbook does something similar with traces, but he decided to do a lot more. You can look at the textbook, you look at the examples, and look at the way he does his traces and stuff. But he does. I think it's overkill. But I'll leave it up to you. If as you look at the text, you need more traces by doing either more traces the way I did or doing the way he does. He looks at like general traces like z equals a constant k, and then looking at what the traces are for different values, all different values of k or whatever. Or you can just do a few traces until you get a curve that matches what your brain tells you the thing should look like. Okay, I think that's the best bet, but I'll let you be the judge. Again, it's not about me learning this stuff. I already know this stuff. It's about you getting this stuff down. Okay, so let's sketch z equals x squared plus y squared. All right. Well, let's decide on the first trace we're going to look at. The first intersection of a plane parallel to the coordinate axes, and coordinate planes rather, and our actual surface. Let's look at z equals 1 again. Horizontal plane, 1 unit above the xy plane. Let z equals 1. I get the same thing we got before. X squared plus y squared equals 1. I get another circle. Okay, so let's get this started. Here's the YZ plane. Here's the x-axis popping out for us to give us 3 space. Here's y equals 1. So So go 1 unit to the right, 1 unit to the left, approximate. And there's our oops. There's our cross section. It's the same. I've been drawing this thing 3 times and it's still looking the same. That's all right. I'll just give up. There's our circle. I don't want to give up. I want to do this one more time. Ugh. Like I should have just stopped while I was ahead. Okay, so there's a circle. X squared plus y squared equals 1, but it's lifted up 1 unit. It's lifted up 1 unit above the xy plane. Okay. YZ. I really don't like my. This is the time when I should probably do things off camera, but I don't want to do things off camera. I want you to see exactly what I have to go through, and that it's normal. Okay, all right. Best I'm going to get for right now. So, is this trace enough for us to understand what this thing should look like in 3 space? No. Let's take a look at what's going on in the xy in the yz plane again. Let's let x equal 0. X equals 0 puts us in the yz plane. If x equals 0, I'm looking at z equals y squared. That's a parabola in the yz plane. Not in the xy plane, but in the yz plane. Well, the yz plane looks just like the xy plane looked like for us forever. It's flat. And there's a parabola that opens upward. We'll draw a parabola that opens upward. And immediately I think you get an idea of what our surface looks like so far. Now for our first surface, we were allowed to, not allowed to, but we did. We also let z equals -1. Okay. Let's sort of let slip out that a problem with that here. Let z equals -1. We can't. We get -1 equals x squared plus y squared. You have the sum of the squares of x and y on the right. Sum of squares. That's always non-negative. There's no way you can get -1 by taking x and a real x value, squaring it, adding it to a real number y and squaring that. It's not possible. This is impossible. Impossible. Look at our original surface. It's z equals x squared plus y squared. That z value had better be non-negative. We need z to be greater than or equal to 0. Okay. So what you're looking at is it. This is our surface. If you're not sure about it, take different find different traces. Let z equals 2 or 1, or we already did 1, z equals 1/2, etc. All you're going to get are more and more and more and more circles. If you didn't get what I just said, and now I get a nice circle. That's it seems if I go fast, I get a nice circle that's horizontal. If you were to draw more and more traces, all you would see are these guys. You would see more and more and more circles. How do I know that? These traces are all z equals a constant. If I put z equals, this is what your author does. If I put z equals a constant into the equation of my surface, I get x squared plus y squared equals a constant. Those are circles. Those are circles. Okay. If you needed, you could also, for another trace that's not a circle, you could let y equal 0. See what's going on in the xz plane. This is a trace of the surface in the xz plane. Let y equal 0. If you let y equal 0, you get z equals x squared. Go back to our surface. Get rid of that. Go back to our surface. in the XZ plane, I'll put it in blue. That parabola, z equals x, that is a parabola, z equals x squared. Kind of ugly, but in my drawing. Okay. Okay. So the general form. Remember how we graph these in practice is to recognize the form so we get a snapshot in our head of what our graph is going to look like ahead of time. Then we fine-tune that by looking at traces and connect the traces. Okay, so the general form. This thing, by the way, is called an elliptic paraboloid. Elliptic paraboloid. The traces of an elliptic paraboloid in planes that are horizontal are ellipses. Ours were special ellipses. They were circles, but they're ellipses. The cross sections with horizontal planes are ellipses. General form. And here's where your memorization comes in. A lot of memorization. Oops. One, well, in general. General form. This is not z squared over c squared. It's z over c. Equals x squared over a squared plus y squared over b squared. The a squared and b squared are affecting the cross sections as in terms of the ellipse that you get with the cross section. What does the c do? What does the c do? Well, let's look at c equals -1. A equals 1, b equals 1, c equals -1. That is an elliptic paraboloid. By the way, when the cross sections of an elliptic paraboloid are circles, very often, in fact, most often, you'll see the word elliptic removed and just called a paraboloid. Paraboloid. Okay, so if you call an elliptic paraboloid a paraboloid, that's the special kind of paraboloid where the cross sections are circles. Okay, so what happens if I let z equals -1 or c equals -1? Multiply both sides by -1 and you'll see. If I multiply both sides by -1, what is the effect? What is the effect? Now I'm going to put some arrows on this, and I'm going to explain the effect as I draw these arrows. The z values are now the opposite of what the z values were before. The z values are the opposite of what they were before. Now, which way do z values go? Do they go right, left? Do they go forward or backwards? Or do they go up and down? They go up and down. On the paraboloid before, where the equation didn't have the -1 factor, the z values went up. So what does that do? It does the same thing that multiplying a function by a negative did. It flipped it upside down. The technical term in pre-calc was it reflected the curve in pre-calc, not the surface, but the curve about the x-axis. So the z equaling -1, in this case, reflects the paraboloid not about the x-axis, but about the xy plane. So this thing opens down. So our graph is in fact going to be, we predict a paraboloid that opens down. I don't know why I'm graphing this in red. X, Y, C. Here's that little opposite here. Opposite. Okay. So what if z was 2? What if, I'm sorry, c was 2? C over 2 equals x squared plus y squared. Now z equals 2 times x squared plus y squared. What did multiplying by 2 do? It stretched the curve in pre-calculus away from the x-axis by a factor of 2. If you missed all that, if this is z equals x squared plus y squared, then this should be z equals 2 times x squared plus y squared. Stretches it out, stretches the surface out. What would this one represent? What would the equation of this be? Just come up with a guess. I think you have the guess. That one might be z equals 1/2 x squared plus y squared. Stretches toward the, in pre-calc, that was a fraction stretched the curve toward the x-axis, a proper fraction multiplied by the function. Okay, so these transformations are old, I'll put them in quotes, friends of ours, and they do the same thing with surfaces as they did with curves. Okay, so how do you get the exact shape? You draw traces. You let z equals, say, take z equals a constant, take x equals a constant, take y equals a constant. Look at different traces and connect the traces until you get a shape that is what you predict should happen. Okay. So here's a brief summary. So z squared over c squared, z squared over c squared equals x squared over a squared plus y squared over b squared. Those are cones. And then z over c equals x squared over a squared plus y squared over b squared. Those are elliptic paraboloids. When a and b are equal, cross sections are circles, so we just call them paraboloids, or you could still call them elliptic paraboloids. So now what if I change the third one, change up the third one a little bit, and change that plus sign to a minus sign? What do I get when I change that to a minus sign? Okay, so that's our next topic. I'm going to look at a special case. I'm going to look at a special case where c equals -1. So example, let's say sketch. C equals -1. So z over -1. And a and b are both 1. So x squared minus y squared. So the one I'm going to look at is z equals y squared minus x squared. If I multiply both sides by -1, I get z equals y squared minus x squared. Okay. Why am I letting z equal -1? Because this is probably the hardest surface to draw for me, and it's easiest or least hard when the y squared term comes first for me, just for me. Okay, so let's dig in. The first thing I want to do is see what happens when I let x equal 0. I want to see what's happening in the YZ plane. The YZ plane is familiar to me. Why? Because it looks just like the XY plane did. And that's where I spent most of my time in Calc 1 and Calc 2 and Pre-Calc and Trig. I spent it in the flat plane. Okay, I guess all planes are flat. In the XY plane. Okay, or in a plane oriented like the XY plane. So I want to look at traces, a trace in the plane, not z equals 0, but x equals 0. X equals 0, the YZ plane. So I'm going to get z equals y squared. Z equals y squared. What does that look like? It's a parabola that opens up. Okay, so let's do that. Same old parabola that opens up that we've looked at. Tons of different times. Tons combined with dozens of times. Okay, onward. So what does z equals y squared look like? Well, if I call this z equals 1, I call this z, this is the y-axis, and maybe call this y equals 1, y equals -1, I get our old familiar parabola. Okay, so there's e equals y squared. Is that enough to know what the surface looks like? Oh my goodness, no, not even close. So let's take a look at what happens when, here's our x-axis by the way, when z equals 1. Let's take a look at let's take a look at the trace of this surface in the horizontal plane. Z equals 1, or in simpler terms, let's see what the cross section of this surface with the horizontal plane z equals 1 is. If I let z equals 1, and this is where I think a lot of students might have a little bit of a difficult time, because of the curve that results is not one you see real often in calculus. And this is the hyperbola. Y squared minus z squared equals 1. This is a really quick reminder in a real basic graph. Y squared minus x squared equals 1 is a hyperbola that opens up and down. So I'm not drawing any of the asymptotes or anything, just keeping it real simple here. Here's 1, here's -1. Okay. So that's the trace in the plane z equals 1. But I need to reorient this thing. This hyperbola that opens up and down in the xy plane is going to be graphed in perspective in 3 space in the plane z equals 1. Oh my goodness. So how are we going to do that? I'm going to use some red to help me out. Here's dotted line. Oops. We draw that dotted line a little bit. Dotted line where z equals 1 in the yz plane. And I want to draw on that dotted line, or with that, the help of that dotted line, I want to draw this hyperbola. Okay, so that hyperbola will open in the y direction. Notice I'm not saying up and down, I'm saying in the y direction. It'll open in the positive y direction. It'll open in the positive, let's see, I'm not getting that positive y direction down real well. In the positive y direction. It will open in the negative y direction. Okay. I'm convincing myself that I've got that okay. Yeah, so this hyperbola is now there. I'm only laughing because I'm sort of reflecting on what I told you about doing this for 30 years, and it still doesn't turn out like the way my brain would like things to turn out. So that's okay. I'll stop complaining. All right. So let me get rid of the hyperbola off to the side here. I don't want to do any of this stuff off camera. I want everything to be done on camera so you see exactly what I'm going through. I want to add a little space. Okay. Is this enough? Not really. Not really. This isn't enough. So let's take a look at what happens in the xz plane. Let's take a look at the trace of this surface in the xz plane. What's the equation of the xz plane? Well, in the xz plane, y equals what? In the xz plane, y equals 0. So that's the equation of the xz plane again. So if I let y equal 0, and again, here's my original surface. If I let y equal 0, then I'm gonna get z equals -x squared. Z equals -x squared, which we all know is a parabola that opens downward in the xz plane. so I need to put that parabola in 3 space in perspective. So in the XZ plane, I'm going to draw that. Parabola that opens down. Parabola that opens down. So why did I draw the piece like that? Why didn't I draw it like that? Because I wanted to draw a portion of it in true perspective. The same reason why I didn't draw the hyperbola earlier like that and like that. I wanted it to be drawn in proper perspective. Okay, and how did I know that was a proper perspective? I'm doing the same thing over and over and over for 30 years. You don't have quite 30 years, but you should have enough time to do pretty well. Okay, is that enough? No, not really. It's sort of getting there, but not really. So let's look at traces in planes parallel to the YZ plane. Let's let x equal, let's say 1. In fact, let's let x equal plus or minus 1. What am I doing with that 2 at once? Well, look at the equation of my surface. The surface is z equals y squared minus x squared. So if I put in the 2 planes, one plane in front of the YZ plane, x equals 1, one in behind the YZ plane, x equals negative 1. Look what happens when I put them both in the surface at the same time. Y squared minus plus or minus 1 squared. I get z equals y squared minus 1. That's a parabola shifted 1 unit down. That would, if I plot that in the YZ plane, if I were to plot that in the YZ plane, that'd be a parabola opens 1 unit down. But it's not in the YZ plane. It's in the 2 planes, x equals plus or minus 1. Okay, so when x equals 1, I have z equals y squared minus 1. I'm going to draw that parabola in the forward plane, the plane that's 1 unit forward from the YZ plane. I'll draw it in red. I might have to redraw it, but there it is. Okay. But I also get one unit behind the YZ plane. Here's the x-axis pushed backwards at negative 1. So I'd also get another copy of that here. Do you see it yet? Piece of macaroni that's sliced in half, I guess. No, that's not going to work. That description didn't work. The drawing's okay. You may not see it because my drawing capabilities. Here's the drawing again, formed all at once. I got that parabola up. I got the hyperbola. I got the z equals negative x squared. And I connect these two. Here we go. I'm hoping you see a saddle. I put the axes back in. Y, negative y, z, negative z, x, negative x, y. I'm hoping you see a saddle. Now, don't laugh too hard because I'm going to try to put the horse on here. Here's the rest of the horse. Here's the head of the horse. Here's Oh my goodness. I don't think I can draw the butt of the horse. Here's the butt of the horse. I'm sorry. Do you see a horse? Okay. That's really the worst horse I've ever drawn. Okay, whatever. Very often this is described as a saddle. So it's sort of a saddle-shaped object with the horse's head pointing in the direction of the positive y-axis. Okay, I also could have drawn the horse's head in the negative y-axis, but this is a perfectly good way to memorize it. It's a saddle that the horse's head is in the positive y-axis. It's not called a horse's head though. It's called a hyperbolic paraboloid. It's called a hyperbolic paraboloid. Hyperbolic paraboloid. Saddle shape. Saddle shape. So, I kind of indicated how you memorize the shape. Z equals y squared minus x squared. The axis of the saddle is the z-axis, and that variable comes first. The axis. The rider, the cowboy or cowgirl would be sitting in the direction of the axis, and the first variable tells us the sort of the direction of the if you're going to consider this a saddle, the head or tail. If you want to have the tail going the other, or the head, reverse the head and tail, you've got the same thing. Okay, if you don't want to memorize it as a horse's saddle, that's fine, but the position of the variables do indicate the shape or the direction of the shape. And yeah, this is called a hyperbolic paraboloid, and that the general form of hyperbolic paraboloid is, so I'm going to take the question mark off this. I can redo it here. The general form, z over c equals x squared over a squared minus y squared over b squared. So why did I do with c equals -1? Because I find it very difficult, again, I mentioned this about an hour ago, I find it very difficult to graph surfaces that are coming out of the page in the x direction. And the x variable would be in the first position. That would mean the direction of the head would be in the x direction. And I find it very difficult to draw that myself. So I memorized the hyperbolic paraboloid with y squared coming first. But this is the general form. The general form has the x squared coming first. General form of a hyperbolic paraboloid. Okay. Now we have some good news and bad news. What do you want first? Well, since you don't get a vote, I'll tell you I'll give you the bad news first. We have 3 more forms to look at. So what's the good news? They're not as difficult as the hyperbolic paraboloid. In fact, the last 2 forms are a little elaborate, but not too bad. But the one we look at next is the easiest of all the forms, I think. So here, let's dig in. For example, let's sketch. Let's see, I want to do this in the easiest way possible. Let's see, I'm going to go off camera to pick the best example. Okay, I think I got a good one. So sketch x squared over 4 plus y squared over 16 plus z squared over 9 equals 1. So here's a real quick way to maybe get an idea of what this looks like. If you don't get this real quick way, it's okay. We're going to do it real slow. But What do you get if you remove the x term? Or let's say remove the z squared term. You get x squared over 4 plus y squared over 16 equals 1. That's an ellipse. If you remove the x squared and leave y squared and z squared, you get an ellipse. If you get rid of z, I'm sorry, you get rid of, which one did I say? If you get rid of the z, you get an ellipse. If you get rid of the x, you get an ellipse. If you get rid of the y and leave x and z, you get an ellipse. So no matter how you slice it, no pun intended, but that's really what we're doing. No matter how you slice this with planes parallel to the coordinate planes, the x, y, y, z, and x, z planes, you get ellipses. What is this? It's a football. It's a football. Okay? If you don't see it, don't worry about it. It's just a quick sort of preview. Let's look at the trace of this surface in the xy plane. When z equals 0, that means I'm slicing the surface with the xy plane. And I get x squared over 4 plus y squared over 16 equals 1. Okay, let's graph that. It's an ellipse. A real simple ellipse. Maybe I'll come down here. That's all right. And ellipse. So here's the x-axis. It got crooked. I should have stuck with it because when I try to correct my drawings, they usually get worse. Oh, that's not so bad. Okay, so let's let, there's x squared, I'm sorry, x squared over 4 plus y squared over 16 equals 1. So, how do you graph an ellipse? And this is the standard form of an ellipse. You look under the x term, take the square root. I mean, you go plus 2 and minus 2 in the x direction. Look under the y. Take the square root of 16, you get plus or minus 4. 1, 2, 3, 4. There are 2 square roots of 4. Oh, sorry, square roots of 16 plus or minus 4. 3, 4. So let's get that ellipse drawn. I'm nervous. I'm truly nervous. Yep. Maybe I should just go for it. Here it is. Here's the lower part. Could have been worse. It's the best I can say about my drawing, is that it could have been worse. Okay, so there's the ellipse. X squared over 4 plus y squared over 16 equals 1. I really don't like my drawing. That's okay. Let's take a look at another cross section. Let's find another trace. Let's let x equals 0. In the yz plane, that's where x equals 0. So when x equals 0, I get y squared over 16 plus z squared over 9. 9 equals 1. Look under y. The y term, you get 16. Square root of 16 is plus or minus 4. Those are both already not marked off on the y-axis. Look under the z. You see 9. The square root of 9 is 2 square roots of 9, plus or minus 3. 1, 2, 3. 1, 2, negative 3. So we're in the yz plane now. In the yz plane, maybe I'll draw that trace in red. Maybe I'll try to draw that red. And there it sort of is. Maybe draw that one again. Seeing a football? Ugh. That's the worst looking football. Okay, one more trace. Let's get another cross section. Let's get a cross section in the xz plane. Let's let y equals 0. If I let y equals 0 in my equation, remember our equation is still here. If I let y equals 0, I get x squared over 4 plus z squared over 9 equals 1. X squared over 4 plus z squared over 9 equals 1. It's not going to be tough to graph this one because we have all the traces, or all the intersection points of this ellipse with the axes already marked off. So under x is 4 plus or minus square root of 4 is 2 squared root of 4 plus or minus 2. Underneath z is 9 plus or minus 3. Those are marked off. So in the xz plane, I will draw a nice, well, I shouldn't call it nice, I'll draw a blue ellipse. Blue ellipse. Whoa, that's not good. Here. I'll draw this one dotted because apparently we can't see it. And maybe I'll go back and put this one as part of the other ellipse dotted. Oh, now it's turned out a little better. Anything else need dotting? No. I sort of see a really kind of cruddy looking football. We don't call it a football. We call it an ellipsoid. Ellipsoid. What does oid mean? Well, part of that part of the word means like. It's like an ellipse, ellipse-like. So cross sections are all ellipses. Okay. The traces are all ellipses. Okay. General form. It's a real easy one compared to the others. The general form, x squared over a squared plus y squared over z squared. Ooh, soups. Y squared over b squared plus z squared over c squared equals 1. Ellipsoid. So before we look at our next form, what do we get when a, b, and c are all equal to the same thing? They're all equal. What do we get when a, b, and c are all equal? Let's say a, b, and c are all equal to r. The same letter, the same variable r. You'll see why. If you haven't figured it out, you'll see why I used r. Multiply both sides by r. Get x squared plus y squared plus z squared equals r squared. That's a sphere. A sphere is like the worst football, but it is a sphere. An ellipsoid, the special case of ellipsoid is a sphere. A sphere. Okay. We're rounding out this lecture. We're in the final stretch. Two more forms. They're a little more difficult than the ellipsoid, but they're similar to each other. Okay, so example. Here's an example of the form before I give you the form itself, the general form. So let's sketch x squared plus y squared, starting out like an ellipsoid, minus z squared equals 1. And it seems like when we have minus something squared, we get hyperbolas out of things. Seems like it. It's actually true. We're going to get some hyperbola action out of this, if there's such a thing. Hyperbola action. Okay. So, let's take a look at traces of this surface in two separate planes, z equals plus or minus 1. And I'm only doing that because when I square plus or minus 1, I get the same thing. So I can take care of two traces at once. I get x squared plus y squared minus 1. I'll even put it in there. Minus plus or minus 1 squared equals 1. So x squared plus y squared minus 1 equals 1. I get x squared plus y squared equals 2. What is that? Circle? If it was in the xy plane, it would be a circle centered at the origin of radius not 2, but radical 2. Let's get that trace. Actually, those traces, because remember we looked at z equals plus or minus 1. Let's take a look at those traces. So here's the yz axis. Here's yz plane. Here's the positive x-axis coming out at us. z, and let's let z equals 1. So let's call this z equals 1. This z equals -1. So this is it. The traces are circles that are lifted both 1 unit up, z equals 1, and 1 unit down below the xy plane, z equals -1. Circles, radius equals radical 2. Radical 2 is about 1.4. So from z equals 1, I'm going to move 1.4 units to the right and left. That's 1.4. 1.4. So we're going to get, I'm going to draw a little horizontal line to help me. The more guides I can have, the better. Let's do that. Okay, there we go. Here's a circle. It's supposed to be a circle of radius radical 2. Maybe I could draw a better one. I think it turned out almost exactly the same. One more time. And it turned out almost the same again. Okay, so let's do the same thing down at negative 1. Let's see. Wow. That's all right. It really isn't, but we'll take it. Yeah. Maybe redraw that one too, so at least they look similar. Okay, I'll take it. Okay, let me get rid of the little vertical lines. Dotted lines. So, let's, is this enough to understand what the surface looks like? No, not really. I barely understand what the traces look like. Okay, so let's I don't know why I did that in red, but that's okay. Let's take a look at another trace. Let's take a look at what's going on in the xy plane. Let's let z equal 0. Okay, z equals 0 is in fact in the xy plane. If z equals 0, I get x squared plus y squared equals 1. Now that's a circle. It's the same old unit circle we're familiar with. Oof. I was thinking maybe if I drew it fast it would work out. Nope. Slow it down, Leon. I'm going to draw this dotted because I happen to know we're going to need it dotted. I happen to also know, you'll be seeing this, why? You'll be seeing this too. I also know that the little portion of the circle down below is going to need to be dotted. Okay, so I got my 3 circles. Let's see what's going on in the YZ plane. In the YZ plane, x equals 0. Okay, so when x equals 0, I'm getting y squared minus z squared equals 1. That's a hyperbola that opens in the direction of the first variable. It opens in the y direction. It's a hyperbola. I'll draw it in blue. It opens in the y direction. And that really clenched it. That I can actually, even with my terrible traces, I can see that. I think. What does it look like? It looks sort of like a nuclear reactor. What do you see in not a reactor, but it looks like the towers in a nuclear power plant. Okay. This is called a hyperboloid of one sheet. Hyperboloid, excuse me, of one sheet. You can think about the word sheet as being one piece. Hyperboloid that happens in one piece. I'm going to say that again. Hyperboloid that happens in one piece. as opposed to what? Hyperbole that happens in 2 pieces or more pieces. Okay, it's general form. General form. X squared over a squared plus y squared over b squared minus z squared over c squared equals 1. Okay. So hyperboloid of 1 sheet as opposed to what? Hyperboloid of 2 sheets. Let's take a look at our last example. Our last form. X squared, just like before, plus y squared, just like before, minus z squared, just like before. What's left? Equals -1. Okay. Notice the signs in the hyperboloid of 1 sheet. Plus, plus, minus, plus. Hyperboloid of 1 sheet has 1 minus sign. I'm going to tell you the name. I think I did already. This is going to be a hyperboloid. Our current iteration of this is going to be a hyperboloid of 2 sheets. Plus, plus, minus, minus. Hyperboloid of 2 sheets has 2 minuses. That's a good way to memorize the form, even though I haven't given you the general form yet. Well, the general form is going to be the same as the hyperboloid of 1 sheet, but there's going to be -1 on the other side. If you didn't catch that, don't worry about it. Just let's get this thing graphed, and then we'll look at the final form, and then a couple words and wisdom, I guess, and then we'll call it quits. Okay. Let's look at traces of this surface in different planes. Let's take a look at what's happening in the xy plane. Let's let z equal 0. Let's let z equal 0. We get x squared plus y squared equals -1. And there's something wrong with that. Well, there's nothing wrong with it. It's just impossible. I guess it is wrong then, huh? It's impossible. So there's no graph in the xy plane. This surface does not, there's no part of this surface in the xy plane. Okay, in fact, let's look what happens if I take the original equation. Oops. Look at what happens if I take the original equation and take the z term to the left-hand side. I add z squared to both sides. X squared plus y squared equals z squared minus 1. What's the smallest I can make z? See, on the left-hand side you have x squared plus y squared. That's always non-negative. So the smallest I can make z would be 1. So that z value needs to be more than 1. I could make it equal 1. But if you can also square it, so z could be also less than or equal to -1. You cannot let z be anything between -1 and 1. Z between -1 and 1 is impossible. Because x squared plus y squared, the thing on the other side needs to be positive, and z squared minus 1 would be negative. So there's no graph of this surface between the 2 horizontal planes. Z equals -1, 1 unit below the xy plane, and z equals positive, 1 unit above the xy plane. Oh. So let's look at the extremes then. Looks like z must be either greater than or equal to 1 or less than or equal to negative. Let's see what happens when z equals 1. Well, I get x squared plus y squared equals 0. That means x and y both have to equal 0. That's a single point. 0, 0, 1. Let's handle z equals -1 at the same time. I still get x squared plus y squared equals 0. I get x and y must both equal 0. I get 0, 0, negative 1. So we have a start to this. It's not a big start, but it's a good start. Here's the YZ plane. Here's the positive x-axis at least. Here's z equals 1. Here's z equals negative 1. I get 2 dots. Is that enough for this surface? Oh, no, I was being sarcastic. That's definitely not enough for this surface. So we need more. Well, we can make z more than 1. So, what should we let z equal? 2. Let's let z equal 2. Let's take a look at the trace of this surface in the plane z equals 2. I'm going to get x squared plus y squared equals, might as well use the form of the surface x squared plus y squared equals z squared minus 1. If I let z equal 2, I have x squared plus y squared equals 2 squared minus 1. I get x squared plus y squared equals 3. That's a circle. Circle. Radius equals square root of 3. About 1.732 or 1.7 about. Okay. So when z equals 2, here's z equals 2, I'm going to get a circle of radius 1.7. Let's do this. Here's a circle of radius 1.7. That's not so bad. Finally. But I get the same thing if I let z equal negative 2. So when I let z equal negative 2, I get the same thing. I get another circle, a radius radical 3. Now my circles, horizontal circles, are turning out pretty good. Whoops. I just graphed it in the wrong place. What a shame. Right after I'm boasting that my circles are turning out well. Okay. This is happening at z equals negative 2. Here, here. Wow, not bad. Is that enough? My goodness, no. That's not enough. I don't see a surface yet. I see a couple circles and a couple dots. Let's see what's going on in the YZ plane. Let's see what's going on in the YZ plane. In the YZ plane, that's where x equals 0. Okay. I'm going to use the version of my surface that I circled in a big red circle. X squared plus y squared equals z squared minus 1. So, maybe I'll use the original form. X equals 0. The original form here, circled. Yeah, doesn't matter really. Okay, so let's let x equal 0. I get y squared minus z squared equals negative 1. Y squared minus z squared equals negative 1. It is a hyperbola, but it's not in the standard form. If I multiply both sides by negative 1, I get z squared minus y squared equals positive 1. That is a standard form of a hyperbola that opens in the direction of the first variable, which is z, in the z direction. Hyperbola opens in the YZ plane in the z direction. Opens up. Opens up. There's opening up and opens down. Z direction. I see 2 cups. Like that movie, was it The Sixth Sense? No, I don't know if that was. I see dead hyperbolas. Sorry, folks. I'm recording this at very early in the morning. I don't mean like 8 in the morning. I mean like at 2 in the morning. So my jokes get really bad. Okay, so I see a hyperboloid of two pieces. This is called a hyperboloid of two sheets. Hyperboloid of two sheets. Hyperboloid of two sheets. Okay, general form. General form. General form. X squared over a squared plus y squared over b squared plus z squared over c squared. Oops, not plus c squared over c squared. Minus z squared over c squared equals -1. Okay. And again, if you look at the pattern of signs, it's plus, plus, minus, minus. It's a hyperboloid of two sheets, and there are two minus signs in sort of the pattern. Okay. That just about ends the lecture. It's not too rough to graph these things once you have the forms memorized, or if you have the forms in front of you, if you have access to the forms. You just identify the form and then look for traces that back up what you think the thing should look like. Okay. Now the video's finished, but so if you want to quit, you can quit. I'm just going to list a summary of the different surfaces. Okay, there were z squared over c squared equals x squared over a squared plus y squared over b squared. These are cones. Z over c equals x squared over a squared plus y squared over b squared. These are elliptic paraboloids. Then the tough one for me, z over c equals x squared over a squared minus y squared over b squareds. These are the saddles, or the hyperbolic paraboloids. Okay. Cones. Paraboloids, elliptic paraboloids. Hyperbolic paraboloids. Saddles. Then the simplest of all, x squared over a squared. One of the more difficult ones for me to graph, because drawing ellipses in different perspectives is difficult for me, but really kind of the easiest one to understand are the ellipsoids. Footballs. Whoa, that's like the sausage football. Okay, whatever. Hyperboloid of one sheet, x squared over a squared plus, so same. Oh, look at the forms, they're similar. Ellipsoids. Y squared over b squared minus z squared over c squared equals 1. Hyperboloid of one sheet, one piece. Okay, and finally, the last one, hyperboloids of two sheets, plus, plus, minus, minus. Hyperboloid of one sheet, plus, plus, minus, plus. Hyperboloid of two sheets, plus, plus, minus, minus. That gives you your portion that opens up, portion that opens down. I'll put the axis in here. And that ends our lecture for this evening, or whatever time it is for you. And as usual, I am looking forward to talking with you again soon.